Okay, it's time. So this is the second problem set, right? It's again due next week at the end of the week. And there'll be a quiz. I'll be sending out a quiz. Forgot about that. I'll be sending out a quiz probably later on today, right? And it'll be due, I think it'll be next Tuesday, similar to the first quiz. Okay, so the first problem here involves a mass on a spring. And the information we're given is that this is in static equilibrium here, with a half a kilogram on the spring. When the mass is increased to 0.7 kilograms, the equilibrium point shifts down 4 centimeters. Okay. And when you see something like that at this point, you should feel that you can determine the spring constant, right? Does everybody feel that? Okay, here's how it works. In terms of this coordinate here, a spatial coordinate, I've called it y, the magnitude of the force exerted by the spring will be proportional to the displacement from equilibrium, and the constant of proportionality is the spring constant. So this is really not quite correct, right? Because we're going to have some unstretched length of the spring in general. But it's not going to matter, because to apply this equation here, which is Hooke's law, essentially, to the information we're given here, what we care about is the change in distance and the change in force. You can see that when we take the change in force and the change in distance, this drops out, it's not relevant, and it allows us to determine the spring constant. Just the change in force divided by the change in positions, or the change in displacement. So the change in force here, the force is mg, it's the weight. So the change is going to be given by this. This is in SI units. The displacement here, the change in position, is 4 centimeters or 0.04 in SI units. So we get 49. We could add another figure, I don't know. We get approximately 49 newtons per meter. So that's the stiffness. That's the spring constant, or stiffness. If we go back to this situation, we know the mass, we know the stiffness, we can determine the frequency of oscillations, the frequency of free oscillations, undriven, undamped. And that's just the square root of the stiffness divided by the mass, so we get 9.9 radians per second. Okay, it's also called the natural frequency, right? Let's see, I think we're given that the relaxation time here, the time it takes the amplitude to fall to 1 over e of its initial value, is 1 second. That means the damping parameter is going to be 1 inverse second, because it's just 1 over the relaxation time. Remember that? So that's our damping parameter. And I think we're asked to find the mechanical resistance. This is the definition of the damping parameter. This is the convenient combination of mass and mechanical resistance to describe the motion. So now that we know what this is, we can find the mechanical resistance. That's straightforward, and it happens to be 1 kilogram per second. And knowing beta, so now we can forget this, I think, because beta is the convenient parameter here. We can find the damped frequency. And even though beta is just about 1/10 of omega naught, because it enters quadratically here, the effect on the frequency is small. It's about 0.5% down from the free frequency. So you saw that we discussed this several times. You actually saw that demonstration, right, where we couldn't see any change in frequency. That was just a coincidence. But it's typically very small because of the square here. So most people just don't worry about this. Almost always you can just drop that. Now we're not through here. The problem asks for what the displacement, this is the displacement or the position for decaying oscillations damped harmonic oscillator, right? That's the general expression with some amplitude and some phase here. And those two constants are set by initial conditions. So our initial conditions here were given that the mass is pulled down that 4 centimeters and released from rest. Okay, so at t is equal to 0, the position is 4 centimeters, and the velocity is 0. So I think the first time I saw this, I can guess what I did. I said, oh, well, the amplitude is going to be 4 centimeters, right? And because it's released from rest, phi is going to be 0. Well, that's only approximately correct. Because of the damping, it's only approximately correct. So let's do this a little bit more accurately than I think the textbook expects you to do. Let's input the initial conditions here. Let's determine the amplitude and the phase here. So at time t is equal to 0, the amplitude is 0.0. The displacement is 0.04. So what that means is, at time t is equal to 0, you can see that a times the cosine of phi has to be the 4 centimeters, right? The other initial condition is the velocity. I take the general expression here, I differentiate with respect to time, and then I set the time equal to 0, and that gives me this expression. So here we have 2 equations. Here's of the initial conditions. Here's one equation, here's a second equation, and we have 2 unknowns. The amplitude A, the quantity A, I don't know if I should call it the amplitude, the quantity A here, and the phase phi. All right, so from you can see we can simplify this. Just kill this. We get this. The amplitude is gone, so we can find the typically what people do here is find the tangent of phi. Divide by beta cosine phi, and we get the tangent of phi as that. Right. Now you'll notice here that because beta is small compared to the frequency, that the tangent's going to be roughly approximately 0, which means that phi is 0. But let's actually find out what it is, not making that approximation. So we just take the inverse tangent of this, and we get, it's about 6 degrees, negative 6 degrees. So that may seem small to you, but it has noticeable effects. So let me comment on that. But before I comment more about this, we need to find the amplitude too. So having found the phase, we just go back to this equation right here. We can substitute in the degrees here, 5.8 degrees. The fact that it's negative is irrelevant here. And we can solve for A. And you can see that A is bigger, right? It's two parts out of 400. It's a half a percent, typical to what we found before, right? With the damped frequency and the natural frequency. So what's going on here? Why aren't we getting what we thought we would get? Well, we're approximately getting this, okay? And the reason is clear, actually, when you look at the graph of what's going on here. Here's this decaying oscillation. It's released from rest, so the slope is 0 here, right? The envelope, though, touches the max points here, and it's going to look something like this. So you can see it's this exponential decay of the amplitude. So you can see that the actual amplitude at x equals 0, which is the 4 centimeters, is not really this quantity A here, right? The quantity A is a little bit bigger. Can you see that on the graph there, the way I drew it? It's a little bit bigger. So this is a small effect, very small effect here. Most people just neglect it. But you'll notice here that this phi here, 6 degrees, things are sensitive to phase, and you can see this. So this may not be a good approximation. It all depends upon what you're doing. There's no universal way to say whether we can set this equal to 0 or not. It depends upon what you're doing, how much accuracy you want. But this can be noticeable, that phase there. Okay. So any questions about that? That problem? Okay, the next one is 7.1. What is the general expression for the accelerate? We're going to focus on acceleration of a damped driven oscillator. And we're looking here at the steady state, right? It's all steady state. So here's our solution. We tend to think of the solution not in terms of x, but in terms of the velocity, right? Because that's the appropriate quantity for impedance. But once we know this, we just integrate with respect to time and get the position. So this is what you want to now think of as the solution. It's preferable to deal with the velocity. And here's the magnitude of the impedance, amplitude of the force. This is the reactance, which is given by this. So we did this in lecture. The acceleration, of course, is just the time derivative of the velocity. So when we do that, the cosine is going to become a minus a sine. The chain rule is going to give us a factor of omega. So there's the acceleration. You can see that the acceleration amplitude is omega times f divided by the magnitude of the impedance. Okay, so what do you think the frequency is that maximizes the acceleration amplitude? The drive frequency. Well, from what we've already talked about, it's going to be typically close to the natural frequency, to omega naught, right? But, we know that we did this in lecture, I think. The drive frequency that maximizes the displacement is, is a little off from omega naught, right? Typically, when there's weak dissipation. So what we're going to do here, and this is a good exercise, I think, is to find the frequency, this is the drive frequency, that maximizes the acceleration amplitude. So here's the acceleration amplitude. F is just a constant, so we don't have to worry about that. We want to find for what omega this is the maximum. So we're going to set the derivative equal to 0, right? Because that'll be where the maximum is. Now, you can do this. I recommend you don't, but you can crank through it. You can make life easier if you think a little bit. But if you want to just directly do this, you can look at the other. I've put into Sakai now, there are the other solutions. I don't know if you guys have noticed that. But in there are some KFCS, some by other professors. There's this document in there. And I think they do it this way. But what we want to do is try to make life easy, because this can get to be messy when you differentiate this. You see omega's buried in here. It's buried in the reactance, right? And we have to differentiate with respect to it. So if you just think a little bit, you can make life easier. If the maximum of this will be the minimum of the reciprocal, the frequency that maximizes this will be the same as the frequency that minimizes the reciprocal of that, okay? And the frequency that minimizes this is going to be the same frequency that minimizes the square of that. That doesn't change where the minimum is. So it's easier to deal with this quantity, because we just have an omega squared down squares, and we've squared this, we've removed the radical here. So what that's going to be is we need to find the omega such that this derivative is 0. We need to get the reactance in there. Rm is just a constant. We need to, and the reactance is equal to this. So when you substitute this in here, I haven't put it in there, what the reactance is yet, just to make this less cluttered. I've simply recognized that x, the reactance depends upon the frequency. So I've taken the derivative, you'll see the derivative of the reactance with respect to omega. And now the denominator is going to be irrelevant. We want to find where this is equal to 0. And finally, I'll then wait till as long as possible, and then I'll substitute in what the actual expression for the reactance is. And the rest of this is just algebra. You can verify it. Okay, if you have any trouble with this, you better contact me. Okay? And finally, we get down to this. And now what we want to do is use the natural quantities here. The damping parameter, We're going to get rid of the mechanical resistance and go to the damping parameter. We're going to recognize the natural frequency, whose square is S over M. And there's our relationship. And we need to solve this for omega. That will be the drive frequency that maximizes the acceleration amplitude. And this is straightforward at this point. Just what we're trying to solve for, it appears in just in one point right here, one position. So we solve for it, and this is what we get. Okay, and again, when the damping is weak, and it doesn't have to be that weak, right, because of the squares here. So even with beta 1%, even with beta 10% of omega naught, which I keep telling you, hoping that it sinks in, it's usually a very good approximation just to forget this. And the frequency that maximizes acceleration is the natural frequency. But it's not exactly that. So everyone keeps this in mind. And when they hit something where, for whatever reason, they have to be very accurate, you then look this up, okay, or rederive it. That's the way it works. So here it is. It's different from these other expressions. Let me remind you. Here's the frequency that maximizes the displacement amplitude. I think we did this in a lecture. Is that right? Does this ring a bell? Here's what we found for the frequency to maximize the displacement amplitude. It's this. The acceleration, it's this structure is downstairs, right? Here's the damped frequency. So they're all a little bit different, right? Typically very low. This has no 2 there. And of course you want to remember the frequency that maximizes the velocity amplitude is just omega 0. That's exact. We haven't made an approximation there. So there are all these different frequencies. Typically they deviate by a negligible amount and people don't worry about it. But everybody knows that if you want to be precise, you've got to go back and look those up. People don't remember them, okay? You just go back and look it up or rederive it. Okay, any questions about that problem? Okay, the next one is 7.5. Okay, so KFCS called this a table. So I get this top view, and I don't know why they called it a table, but we'll go along with them. It's just some body, okay, some object here, and a mass and a spring is attached to it. And some external force is causing the table to have, is driving at a pure frequency omega and is causing the table to have a constant acceleration amplitude. Okay, so some external agent, we don't know what, doesn't really matter, is causing this thing to go back and forth such that this is the acceleration of the table here. All right, so what's going to happen? Now normally when we think of a damp-driven oscillator, we think of applying the force here, right? We've talked about this before. A trick is, you should be able to, at this point to realize, and I think this has actually come up, that this is another way of achieving damped-driven simple harmonic motion, right? But the details are going to be somewhat different. That's the purpose of this problem, is to go through this. Okay, so how do we get the equation of motion here? Newton's second law tells us the mass times the acceleration is the force. Oh, we have no damping here. We'll talk a little bit about damping later, but right now there's no damping. So the force here is just one force. It's the force of the spring. We'll let capital X be the instantaneous displacement of the table from equilibrium. It's going back and forth here. And little x, the mass. And this is measured in the laboratory frame, right? We're not going to, we could, but it's not appropriate in this course to jump into the accelerated frame here. So those of you who've taken mechanics before know that you can solve this by jumping into the accelerated frame. And it's actually easier that way. But you have to know about non-inertial frames of reference, which most of you don't, I have a feeling. Is that right? Well, maybe most of you do, but I doubt if the distance learning students can remember that. They probably had it at some time. So we're going to do this from the laboratory frame of view. So the instantaneous force on this mass depicts, it's minus the spring constant times the displacement of the mass from equilibrium. So that's going to be given. The displacement of this is going to be the displacement of m, and I have to subtract off the instantaneous displacement of the table. So, and you know why? Because if, let's say this is equilibrium and they're over here at some point. If this distance hasn't changed, the force is zero, right? Because the spring is unstretched. So what's relevant here is this difference here. Okay, so let's, how do we proceed here? Well, we essentially know x. We know the acceleration. So we can integrate twice, and we get, integrate with respect to time twice, and we get this for the position. We can then substitute that into here, and into our equation of motion for little x. Okay, now I've naturally defined where I see that s over m is going to be the square root of omega naught, is going to be omega naught squared. So that's naturally appeared due to these two quantities here, right? The mass and the spring constant. They're all relevant is their ratio. So I'm going to call that omega naught squared, which is what it is. Okay. So now let's bring this term over to this side of the equation. Does that look familiar? Yeah, when this is equal to 0, that's undriven, undamped, simple harmonic motion. That's the differential equation for simple harmonic motion with no drive and no damping. So we can see here that what we have is a driven simple here's the drive term. It's homogeneous. There are no x's in there. Okay, now it's a little bit more complicated than what we've seen. But the fact that I have an oscillatory, term here means that we have driven simple harmonic motion with no damping. When we consider the normal way we consider that all of this would be the force divided by the force amplitude divided by the mass. Okay, but this is a different situation here. The force is not being directly applied here. The force is being applied here, some external force. So we found here that we have the same form for a driven simple harmonic oscillator at frequency omega. But this is the drive amplitude. The drive amplitude is frequency dependent. Okay, so as I change frequency, keeping this A constant, let's say we keep A constant, the actual force on the oscillator changes. But that's what we can handle that, It's just a frequency to just carry it along in the calculation. And how are we going to solve this? You know how we solve it. We substitute this complex solution. Oh, you'll notice where are the little underscores underneath the x's? You may have not even noticed it. They're gone. We understand, right? It saves a lot of trouble. We don't need to distinguish now, I don't think, unless it becomes important. We don't need to distinguish between these two quantities, right? So I've just done it without thinking here. We've gone complex here. So there's going to be a steady state solution at the same frequency as the drive. There'll be some complex amplitude times e to the I omega t. So we take this, substitute it in. This, one of the reasons this is a good problem is it takes you through in a little bit more complicated situation what we did in the simple stuff, the simpler stuff which we did in a lecture. So this is ideal homework problem, I think, here. So we want to find the solution here for little x. We take it, substitute it in, and I need to find this complex amplitude. And here is the complex amplitude. Now I'm going to do something for convenience here. It's not a big deal. Normally we think of the complex amplitude as some actual positive amplitude times e to the I phase, right? Well, there's no phase here because there's no damping. The phase is either 0 or 180 degrees. So I'm going to allow my b here. I'm going to allow the real b to be positive or negative. And you can see it's convenient because omega can be on either side of omega naught. It's not just this minus sign here. That's why I'm doing it. The phase here is going to be either 0 or 180 degrees. And I'd rather I'm going to deal with it with a sign, whatever the sign of this is. I don't want to shove it into an exponential. This makes it easier. But of course you can do it that way. The other way. So this is a signed amplitude. It can be positive or negative, our b here. It's going to disappear because we can see that we've solved for b. We substitute the expression in. simplify, recognize the acceleration here, because that's what they're asking for. And here's what we get. You can go through I can't, spend a lot of time going through the algebra here. You can do that. And like I said, if you have any questions, contact me. Here's what we get for the acceleration of the mass compared to the acceleration of the table. That's what they ask for. It's a dimensionless, it's a useful quantity. It's acceleration scaled to the acceleration of the table. It's a very simple function here. And it resonates. Now we haven't talked about resonance yet. We're going to get into that tomorrow in our thorough treatment of oscillators, right? It takes a while. But you can see here that this blows up when the table is being driven at the natural frequency. We have an infinite response, right? And that's, it's not going to happen in reality because there's going to be some damping. Damping, as you increase the frequency here, this mathematically goes to infinity, but dampening is going to cause it to roll over and get something there. On the other side, this ratio here, you can see it's going to be negative. And that just simply signifies that here, the table and the mass are in phase, okay? Like this. See how these are, they're in phase like this. Here, they're 180 degrees out of phase. That's what the fact that this is negative when omega is a greater, wait. Right, when omega is greater than omega naught, this is going to be negative. So this just signifies the fact that they're 180 degrees out of phase. And again, with damping, you'll see this roll over. Damping will also cause the phase not to be 0 or 180 degrees. We're going to go over this thoroughly. We've already have the solution, but we need to talk about resonance next too. And that's what we're going to do tomorrow. Okay, now this actually has an application, but I think it's a little bit too much for now, and this problem set's kind of long, so in the past I've omitted this. And it's a little bit of a stretch for them to put this in at this point, but it is very practical. And people do this. You can utilize this effect that here I am talking about. I'm not supposed to be talking about it. But let's say this is some object that's subject to noise. It's just being hit with vibrations, noise vibrations, and it's vibrating like this. If you want to dampen in a certain frequency, a range about a certain frequency, you can add a damped simple harmonic oscillator here. And that will have the effect of dampening. And this is actually done a lot. The standard example, and this is getting way ahead of the story, but air conditioning ducts can have annoying resonances. So what they'll do is hang Helmholtz resonators off, very similar to an oscillator like this, to absorb the energy, get the amplitude down. Remember what a Helmholtz resonator is? It's if you have a bottle, an empty bottle, and you blow across the top. The switch is the same as that. I think I did that once before. But the point is, if you have some oscillator at that frequency, it'll have the effect of dampening out the energy. But I think if you're interested in this, contact me, okay? I think we don't want to get into it anymore right now. But it'll come up later in the sequence. Okay, any questions about this problem? Okay, so the next one is 8.1. And what's that? It's, okay. So, remember, we took a cosine drive when we did damped driven simple harmonic oscillations. We considered a drive that was a cosine omega t. And we talked about that, how, it could just as well be the sine of omega t. And we discussed a little bit how you would get the solution, and it was kind of vague. Okay, well, now we're going to do it right, okay, properly and precisely. So, in this problem, we have an oscillator that's initially at rest. Okay, there's something missing here. First of all, be really careful with this. The units are not. This is an apple and an orange, but what's missing there? I can't believe it. Yes. So let me write that down. So what's supposed to be there is the position. And normally you wouldn't make such a statement because this is dimensionally incorrect, but when it's equal to 0, it doesn't matter. Okay, so that's what, please add this in here. So that's our initial condition here. And we're going to look at the solution, and it's the solution for all time, for all, time, non-negative time here. So the transient will be in there too. So again, this is one of those problems that educators come up with. They, go through some this is typical in physics, right? It goes through some derivation in the text, and you say, well, this is, how do we get this, help this get sunk in the students' heads? Well, we do a problem, but we just don't want to reproduce the derivation. We're going to do something different. So this is what's different here, is the fact that it's a sine drive. Oh, and we're going to take the special case of driving it on omega on resonance, omega naught. Omega isn't going to be omega naught, approximately resonance. All right, so let me remind you what we did in lecture. We considered this. Now I'm going to be it's important to be explicit here, so I'm going to put the bar, the underscore, whatever it is, yeah, underscore here. So here's the damped driven equation of motion for a damped driven simple harmonic oscillator. And what we did in lecture was we took the real part of this. That's going to give us our actual displacement when there's a cosine omega t drive, right? But once we have the solution to this, we could just as easily take the imaginary part. Okay? We can take the imaginary part of this. The imaginary part is going to solve what we're after, because it's a sine drive. So I take the imaginary part of x. The imaginary part of this will be no I, because I'm just going to take the imaginary part, and I will have the solution to the sine omega t drive rather than the cosine omega t drive. So I think the best thing to do here is just, we know how to solve this, right? It's really easy from the complex exponential point of view. We let x be a complex amplitude times e to the I omega t. And we choose that because then, because of the structure here, the e to the I omega t will cancel. We're going to be able to get a solution. And here's the solution. This is now going to look, well, we did this. We did precisely this. So you can look back. This is the complex x. So we did this. And remember, the magnitude of the impedance is given by this, where here's the reactance, and the phase angle is given by that. Remember that? So now, instead of taking the real part like we did before, we take the imaginary part. And you can see here I've got an I here, so it's going to end up involving the cosine omega t. Okay, now this looks like all, but it's really add, right? Because of Adobe. I don't know, I don't understand this, but this has happened before. This is the steady state solution, but in our problem we need to deal with the whole solution. So we're going to add the particular solution. And the particular solution is independent of the drive. Remember that? That's the solution to the homogeneous equation. So the fact, when this is equal to 0, the fact that we have a sine drive instead of a cosine is irrelevant here. We can just use what we developed before. So you'll recognize this. Here's the transient solution, precisely as we had before in lecture. And I'm going to add the steady state solution right here. And now they ask us to assume weak damping. All right, so I'm going to be, again, a little bit more careful about this because I know from my experience, you don't just want to start setting beta equal to 0 everywhere. It's not, okay. So let's see how this goes. But here's what we've got. The drive frequency is equal to omega naught. that means that the reactance is going to be 0. Here, yeah, so when omega is equal to omega naught, the reactance will be 0. And when we do that, the phase angle will therefore be 0, because the reactance is right there. Here's what we get. There's the transient solution. And here's our solution for a sine drive. Steady state solution. Now we're going to impose initial conditions. Remember these initial conditions here. So I evaluate this. This is the velocity. We're going to need to know this. And you'll notice I'm not going to discard the beta terms. You're going to see why. I'm going to show you why I feel uncomfortable just start throwing away the terms with beta, like throwing away this term. And you'll see why in a moment. So the fact that the initial position is 0 means that this has to equal 0 at time t is equal to 0. So I get this. We went through something similar in a previous problem today. Here's 0 initial velocity. I set this equal to 0. This is going to be gone at time t is equal to 0. So I get these two terms. I can cancel a, because a is not equal to 0. And so what I get here, from here I get the tangent. We've seen this similarly before. The tangent of phi here, this phase angle in the transient solution, is minus beta over omega naught. That's approximately equal to 0, which means phi will be 0. However, we can make the next correction. The tangent, and I didn't say anything about this here, except this little dot, these dots that you see, this dot that you see here. What's the tangent of a small angle, approximately? It's, yeah, the tangent, oh, maybe I should do over here. When you have when an angle is small, the tangent of phi is approximately equal to phi. The tangent approximately equals the sine, and you can, if you just think about a right triangle with a small angle, you can deduce this really easily. When an angle is small, the tangent approximately equals the sine, and they both equal just the angle in radians. We've seen this, I think we've seen this before, right? I think we have. It's the third week and I'm already forgetting what we've done. Okay, so we're going to keep this here, and when you do that, I shouldn't have written this way. I should have written a curly bracket. Here's the solution. Now we have made the approximation. I have made the approximation of small beta in the amplitude here at various places. But you'll note I've kept it here because we've seen better. Remember that problem with the 5.8 degrees? All right. So, and this is what people do. Typically, it's going to be a very good approximation outside here. But in the phase here, you can see that. It'll have a noticeable effect. 5.8 degrees. That was what it was for that other system. I don't know what it is here. We're doing this all algebraically, right? This is all algebraic. We don't have any numbers here, right? So I don't know what it is here. We don't know. We need to specify it. But it's just usually a good idea because here we don't have that small dependence upon beta where it gets squared, right? Like in the damping frequency, where it typically has a very small effect. Here it can be noticeable even though that's small. So you don't need to worry about this. I'm just mentioning it to you in case you ever get involved with it. Most people learn this stuff the hard way. You know, they're doing some experiment and they're saying, "Oh, the phase is not right. What's wrong here?" You know, so we got this weakly damped system, and then they realize, "Oh yeah, I remember that guy who said," I don't know. But so I'm just pointing it out to you. Okay. Okay. Any questions about that one? Okay, so, we're actually doing pretty good here. So those are the main, we have a couple of simple problems here. Those are the main problems. And as I said, you know, the homework is for you, right? I just check it off, right? So you want to get the most you can out of it. It's good to work in groups to do that. I discovered that late as a graduate student. I can't remember if I told you this, but study groups are great. Yeah, ask Professor La Raza. He and I were in a lot of study groups at UCLA. Go through these, and if you had, you know, sometimes I make mistakes, right? This is a pretty stupid one there, but if you have any questions or you disagree with what I've written, just contact me, okay? Okay, so the next one here is 1.92. So we have a damped driven harmonic oscillator, cosine omega t force, and it has speed. They should have said velocity. Technically, speed is the magnitude of the velocity. So they should have said velocity there. Oh, this is the solution, okay? We know, this is how we now think of the solution to a damped driven oscillator. We think of the velocity, because that's the natural variable to look at when you're using impedance. There's the velocity amplitude, capital U. It's the amplitude of the force divided by the amplitude or the magnitude of the impedance. Now, this is a trick. Some of you may have seen this before. Remember when I made a big deal out of saying, if we wanted to find the power involved here, the average power, okay, and they meant, when they say power, capital pi here, they're talking about the average power. They're averaging over time, not the instantaneous. And remember when I made a big deal about how saying we have to take the real part of the power is the force times the velocity, but we've gone complex, so you've got to take the real part of the force and the real part. Remember that? Well, there's a trick you can do so you don't have to do that. I don't encourage you to use this trick, and we're not going to use it. And KFCS don't use it. I don't think they use it at all, actually. I think it's just in this problem. And I won't be using it in future courses in the sequence. But I know it's popular among electromagnetic wave people. And here's the trick. You can, instead of taking, you know, the real part of this times the real part of that, you can go ahead and multiply the complex numbers, okay? But you've got to take the complex conjugate of one of them. It doesn't matter which one. It's easy to show that it doesn't matter which one. And that's the point, I guess, of this problem. You can easily show this. I omitted it because this problem's a little long. But you can easily show that when you have the product of two complex numbers, where you're taking the complex conjugate of one of them, it doesn't matter which one you take. It's easy to show that, okay? So it turns out if you take this with the complex conjugate, then take the real part and put a 1/2 in front of it, you get the right answer. All right, has anybody seen this before? So again, you know, this is just an exercise. It's good to be exposed to it, because if you get seriously involved analytically with this stuff, this is a lot easier than having to take the real part of that and the real part of that. It is easier. But I don't think we're going to be using it apart from this problem. But let's go through it. So we just, because we know what we better get here. So we substitute in the complex force, okay, and the complex conjugate of the I didn't write down the solution here, but this is the it's in the problem statement. Here's the complex conjugate of the velocity, all right? And now you can see what happens here. These two factors cancel. E to the I omega t cancels with e to the minus I omega t. And we get this, and the real part of this is just the cosine of theta. And if you go back and look at the notes or the book, you'll see that this is the average, is identical to the average power. And the reason that we don't recognize it is because this is complicated. But down the road in this course, we're just going to be using the resist. We're not going to be using this directly or I'll be reminding you how the best way to think of it is. The best way to think of it is think of a resistor. What's the rate of power dissipated in a resistor? It's I squared R losses, right? Okay, so it's I squared R. You have to put a 1/2 because that I is the peak, when I is the peak current. You have to put a 1/2. And then we just use our relationship between the velocity, which is in the problem statement here. So we can easily derive this from a very physical point of view. But anyway, we've shown that this method works. And people, like I said, electromagnetic wave people love this. They use it a lot. But there's really we don't use that enough, I think, to justify this. It's better just to take the real parts, like we did in lecture. Okay, any questions about that one? Okay, the final one, there's that formula again, right? Except, where's the angle? Well, let's look at the problem. 1.9.3. All right, this is very close to what we did in class, and this has been screwed up. I screwed this up, or somebody came in my office and screwed it up. So we're missing the cosine of theta here. What's wrong? Steady state, the power dissipated by the frictional force. So the power dissipated by the frictional force is equal to this. This is the force times the velocity. So this is the instantaneous velocity. This is the power that's being dissipated by the resistive force. So this is going to be the average power. And the point of this problem is to do something similar to what we did in the derivation of this formula here, is to substitute in our solution here into here. And show that we get that. So something's wrong. I didn't notice this one. Oh, this is just an equivalent form. Okay, sorry. You'll notice this is not identical to what's before. The cosine of theta, which we're accustomed to seeing, is this is an equivalent to this, because in terms of the mechanical resistance is this. They're mathematically equivalent. So this is exact, and we're not doing any special case here. This is just one, and you can look back, it's in the lecture notes, I'm sure it's in the book. This is one form of the average power dissipated. So the point here is just to verify this with our solution here. It's just an exercise. We substitute in our velocity, which has this really nice form here because of impedance. Impedance involves velocity here. I substitute this in here, take out the multiplicative constants, and we get, do I care what's sitting here? What's the average of a square of a sinusoid? Can you see it in your head? It's 1/2, remember? Yeah, so you want to be able to see that. It saves a lot of trouble. So you can use a trigonometric identity if you want to, but after a while you look at this and you say, that's 1/2. So when we do that, we do get this form of the power. So it works. Okay, any questions about this problem? So we have a lab this week, right? We had to push, we normally don't do it like we normally delay, but Jay is going to be out of town for a couple of weeks. So today's Monday. Is everyone happy with their data? I'm having Jay keep the mass and spring lab. That's going to be set up. He's going to be taking it down shortly, probably tomorrow. So if anybody needs to retake the data, no, you know, in this case, it's really easy to set that up, so you don't worry about it. But in general, the setups will stay up for a little bit over a week. We'll cover 2 weekends, you know, and so it's going to come down pretty soon. Also, distance learning students, there's still some confusion. Distance learning students will be uploading their quizzes into Sakai, as well as their lab reports. And I've sent out a specific message on how that's supposed to be done to the distance learning students. Okay, does anybody have any problems or questions? Now, I want all the resident students to make sure you come by and talk to me about your data, right, and the analysis you have. And I'm doing a similar thing with the distance learning students, although we're trying to handle that, not get into telephone conferences. Those can take a long time. But if it happens, it'll happen. But we're handling it similarly, we're handling it with them, okay? So make sure, I want to see everyone's data, because you can make big mistakes. Believe me, I know this from my experience. All right? Okay, anybody have any questions or comments? Anything? Okay.